All right, thanks everyone for sticking around, and thanks, Mick. The frontier in visual neuroscience isn't just bigger data sets, it's now condition-rich multimodal data resources. The same stimulus sets are now being run across fMRI, EEG, MEG, and many other recording modalities. For example, the Things initiative spans several of these now, and the natural scenes dataset's large fMRI corpus is now being paired with EEG and ePhys measurements using overlapping stimuli. And initiatives like Mosaic are explicitly trying to unify these resources into a common substrate. And on top of all this, there's now an emerging subfield of groups trying to develop foundation models of neural data that learn shared representations across these recordings. So it's all very exciting, but it makes an old problem even more pressing. And as anyone who's looked at neural data sets knows, most of the voxels and electrodes in these resources can look pretty bad. Noise is pervasive, and it places a tax on everything we do downstream: reliability, the fidelity of our models, and our ability to align representations across individuals. But what if we could pay fewer taxes? What if we could better pull out signal from our noisy measurements and have more reliable response profiles, or more identifiable structure in our representational similarity matrices, or EEG traces that can isolate stimulus-evoked effects more clearly? And what if our encoding models had higher variance explained and could provide more interpretable feature visualizations, all without collecting any more data? Today, I'll try to bring this vision to life by telling you about partitioning signal and noise, or PSN, our effort to develop a preprocessing tool applicable across many modalities of neural measurement. And this is work done with a great team spanning many different institutions. Before I get into how PSN works, let's just orient around what I mean by signal and noise. Signal is the expected response across repeated trials. It's the stimulus-evoked variance that generalizes. So if you had 100 trials per condition, then you could just average and you'd be in pretty good shape. And that's what you're seeing here: nice clean tuning curves emerging from lots of simulated data. But of course, neural measurements are very noisy, and there's lots of trial-to-trial variability around the mean. And in practice, we often don't have 100 trials, we might have 2 or 3. And now your averages from the same data generating procedure might look like this: much more messy and unstable and hard to work with. So the goal of PSN is to improve upon just trial averaging when we're in this familiar regime of noisy data with limited trials. First, I'll walk through the process of how we convert a given set of neural measurements into these 2 different signal and noise estimates, and then I'll demonstrate how PSN influences downstream analyses when we use the signal estimate instead of trial averaging. And finally, close by highlighting some strengths, limitations, and practical recommendations for using the tool. Okay, so the first part of the pipeline is trying to estimate the signal and noise distributions that underlie the data. And here's what I mean. We're going to specify a simple generative model of the data by saying that they're approximately multivariate Gaussian and that the noise is zero mean. And so in this generative model, the measurements we get are basically draws from signal and noise distributions. And I'm going to provide geometric intuitions on the right side here. Basically, data is this multivariate Gaussian in high-dimensional space, and then we measure sums from signal and noise distributions, each of which have their own principal directions or eigenvectors. So the input to PSN is a 3D matrix that looks like this, with some number of units, some number of conditions, and some number of trials. And we can schematize that here with these axes corresponding to different units, and we can present some different conditions, in this case images. And if we did, for example, 10 trials per stimulus, we'd get a cloud of 10 dots in this high-dimensional space, and then we could average, and that would give us 4 estimates of trial average responses per condition. So we want to know the shape of these multivariate Gaussians, and the covariance matrices associated with them is what tells us the shape. So in this generative model, we can think about the trial average data covariance as being the sum of a signal covariance component and a noise covariance component. And each of these are unit by unit matrices, and we want to estimate them. The insight of our pipeline is that we can straightforwardly estimate the data covariance from our trial average measurements, and then we can use trial repetitions to estimate the noise covariance structure, which basically tells us how units go up and down together, wiggling around the means of their responses to the different conditions. And then we can subtract noise covariance from the data covariance to infer the structure of the signal covariance. I'll just quickly give you a glimpse of how this looks with real data. This is about 400 surface vertices from the fusiform face area in the natural scenes data set, and this is the data covariance estimate we get. And now when we look at the covariance over the trial-to-trial residuals, we can see that there's quite a lot of structure here across these vertices, and then we can do that subtraction and get our estimate of signal covariance. And this kind of generative modeling framework, this part of the pipeline, was rigorously validated in a publication led by Kendrick Kay last year. So now we've described the structure of the data, but we haven't actually changed it yet. The next step is to isolate the underlying signal that corresponds to each condition. To do this, we'll use our knowledge of the signal distribution and just do low-rank denoising of the data. So we have our signal covariance estimate, and the next step is to do SVD, which gives us a set of eigenvectors and eigenvalues that describe this distribution. Geometrically, the eigenvectors of the signal distribution point in directions where stimulus-driven variance lives in high-dimensional space. And so we can pursue the classic approach where we basically denoise by retaining some top k number of PCs. The key question is how many to retain. And the insight here is that along each dimension, we can quantify how much signal variance and noise variance is present. So we can plot variance as a function of PC dimension, and for signal, we might get something like this. And for noise variance, we might get something that looks like this. And the magic of these signal eigenvectors is that signal variance tends to concentrate in the early dimensions. So now, given this information, the user can decide how aggressively they want to denoise the data. And what do I mean by that? Well, you're going to choose a threshold. And you could imagine choosing to retain all dimensions, and that would basically be the same as trial averaging, where everything stays behind. A conservative approach to denoising would be, let's say I want to retain essentially 100% of the signal, then I might choose exactly the threshold where signal variance hits 0. Or you could push for something even more aggressive and retain fewer dimensions and say, instead, I want to partition out all the dimensions where noise variance exceeds signal variance. And that might be closer to optimal from like a cross-validation perspective. Importantly, the dimensions you get from naive PCA applied to trial average data would not give you this benefit of disentangling signal and noise, and the early dimensions are much more likely to be dominated by noise. And I'll show you an example of this later. So now we've chosen a threshold, and how do we obtain our final data outputs? We finish by taking the trial average data and projecting it onto the top k signal eigenvectors that we just selected. And what comes out is a new units by conditions matrix that lives in the signal subspace, and the difference between that and the original input gives us our updated noise residuals. So that's the whole pipeline. Estimate covariances, get the signal basis, choose a threshold, and then do subspace projection. It's not too complicated. So now let's look at how this works with real data. If you buy what I've told you so far, then a key prediction is that PSN should improve reliability and also improve the stability of various downstream outcomes. So let's look at the same FFA data we were plotting before, and here we're going to use 2,000 conditions to fit PSN, and then evaluate using 515 held-out conditions that are shared across the 8 subjects. And for those 515 stimuli, we'll do leave one trial out splitting and run 3 different reliability comparisons. First, a baseline where neither split is denoised. Then we can look at applying PSN to one split and comparing to held-out noisy data. And then third, we can apply PSN to both splits and see how well the new signal estimate generalizes. So here, for FFA, we see consistent and fairly dramatic improvements where reliability nearly doubles between the baseline and PSN scenarios, and critically, there's improvement even when comparing against held-out noisy data, suggesting that PSN isn't just artificially imposing similar structure across the 2 splits of data. And then we can look at what that increased similarity looks like just for an example voxel in the pool, comparing baseline to PSN, and we can see how the signal estimates tighten around the diagonal and become more consistent. So PSN improves the reliability of voxel tuning profiles in this region, but what about other regions and subjects? Well, we can now look at how that changes across all 8 subjects and 4 ROIs, V1, V4, FFA, and PPA, and we find stable and consistent gains across the board. Intuitively, these benefits kind of mimic the effect of having had more trials available to average out the noise. And the benefits indeed extend to downstream analyses, ROI tuning stability, the stability of representational dissimilarity matrices across the splits, and encoding model accuracy when using a robust ResNet 50 backbone. Here, each dot is a subject, and there are broad improvements over both trial averaging and denoising that relies on naive PCA. So this improved reliability we see also does produce more stable and effective downstream outcomes. Okay, let's shift gears to look at data from a forthcoming massive data set of EEG responses to NSD stimuli. And now our approach changes slightly, and we're going to treat each electrode time point pair as a unit. So now we're learning a spatiotemporal basis for denoising. And I'm just going to show you two electrodes, comparing raw trial average measurements on the left and denoised measurements on the right. And we can do the same kind of reliability analysis, and again, we see consistent improvement, where here, PSN nicely compresses variance in time points where we wouldn't expect there to be stimulus-evoked responses, while preserving and sharpening the post-stimulus response trajectories. And this suggests that PSN is also going to be highly effective for spatiotemporal denoising. It's not just limited to patterns of voxels in space. We can also ask, what does naive PCA do with this kind of data? And I'll just show you the loadings of each electrode and time point onto PC1, comparing the PSN signal basis to naive PCA. And this is what we see. It's pretty dramatic. The first PC from the signal basis shows an expected delay before the loadings increase in magnitude. And for naive PCA, there are clear oscillatory wiggles throughout the time course that capture ongoing non-stimulus-related noise. So this helps us kind of see under the hood of how PSN cleans up the post-stimulus trajectory by separating out different sources of variability. Beyond fMRI and EEG, we're applying this to many different other modalities, including marmoset calcium imaging data from face patches. We're looking at encoding models of macaque IT responses and trying to interpret the features that the models are choosing and how that changes with denoising, and also using human intracranial responses to NSD stimuli. And finally, we are extensively validating PSN using simulated data sets with known ground truth and looking at the bias variance properties of the method. So just to quickly close with some strengths, limitations, and recommendations, PSN is simple and linear, making only minimal assumptions. It's modular, so it accompanies existing preprocessing very well. And it's built for condition-rich data, but it works fine on smaller data sets too. And the user can rely on automated thresholding procedures to safeguard against signal loss. In terms of limitations, you do need trial repeats available. And the denoising benefit may come at the cost of a small amount of signal. That's just the classic bias variance trade-off. And the more that signal and noise distributions tend to overlap in your data, the sharper that trade-off can be. On the practical side, the paper is in prep and will include comparisons between PSN variance, PCA, ICA, and several other methods. And we'd love for people to come help us test the method on your data. The code is in very early beta, and so please come find me if you're interested in applying it. And with that, I'd like to acknowledge our great team of collaborators again, and happy to take questions. Thank you.
Okay, thank you for that talk. We have time for questions.
Yeah, really cool method. So what I didn't quite understand is like, are they, so it's actually two questions. So first, does it rely on any kind of regularization for the covariance matrices? And can you apply this whole brain then? Or is it like, do you have to use it in a region of interest kind of approach?
Both great questions. So first, is there regularization in the covariance estimation procedure? Yes, and that's a key insight. That's a key detail of that technique that I didn't have time to talk about. It's in the paper. The main one is shrinkage of the off-diagonal elements of the covariance matrices done via cross-validation to optimize the generalization of those estimates to held-out data. And then in terms of applying it to the whole brain, yeah, I mean, it kind of depends on what your level of compute is, and also your interests in understanding the different dimensions of representation. So if you're going to apply it to a huge sector, you might think, like, what's PC1 of the entire visual system? Is that going to be relatively coarse? That might be fine. It's possible that you could do a bit more surgical denoising if you look at smaller regions of interest where the components might be more nuanced. But these are open questions, and we're trying to figure it out ourselves now.
We have time for one more question.
So, lovely, clear explanation of that pipeline. Robustness to non-Gaussianity, Poisson, whatever.
Yeah, so great question. The Gaussian assumption is not like 100% stringent. It's likely that one could obtain some degree of benefit even for data sets that have distributions that are slightly non-Gaussian. As far as like full-on Poisson data, that's not what we designed the method for, but it's something we're interested in exploring, that I'm exploring now in simulation, of how far can you push it, and are there modifications we can make to the covariance estimation procedure to accommodate spiking data. So I don't have a good answer for you yet, but soon I will. And then just one last thing is that the kind of safeguards built in to avoid signal loss would help you, even if you used a data set that violated distributional expectations, you can be pretty confident that you're not just going to discard useful signal. So.
Okay, let's thank our speakers again.